Roman concrete or modern concrete, which one is better? Hey, engineering enthusiasts! Today, we're going to unravel a mystery that intrigues a lot of people. Is Roman concrete really better than modern concrete? Everywhere we look, we see the impressive ruins of the Roman Empire. Amphitheaters, aqueducts, temples, and the grand Pantheon with its monumental dome, all bravely standing the test of time. Faced with such durability, it's natural to ask the question, how? These structures, built almost 2 millennia ago, are still standing, while some modern buildings seem to have a much shorter lifespan. This observation leads many to argue that Roman concrete somehow surpasses ours. But is this comparison fair and technically accurate? Let's analyze what makes each of these materials so unique, and which one stands out in different aspects. To understand this issue, we first need to define what concrete is at its core. Concrete is a composite material made from a mixture of a binder, which in our case is cement, that binds the aggregates, such as sand and gravel, with the addition of water. The magic happens when the binder reacts with water, forming a paste that hardens and glues the aggregates together, creating a solid and resistant mass. But how did the Romans achieve this feat centuries before our modern engineering? Well, Roman concrete, known as opus cementicum, didn't use the binder or cement that we know today. Its binder was a special combination of quicklime and, crucially, a volcanic material found in abundance in the Pozzuoli region near Naples, called volcanic ash, or more commonly, pozzolana. In addition, they used aggregates like volcanic rocks, and especially for marine structures, the mixture was made with seawater. The big difference was in the chemical reactions that occurred when lime and pozzolana were mixed with water, and in the case of coastal and marine structures, with salt water. They formed a special type of calcium aluminum silicate hydrate, which researchers call CaSH gel, or calcium aluminosilicate hydrate. This reaction wasn't as fast as that of modern cement. It was a slow and gradual process that could take years to fully complete. The remarkable durability of Roman concrete, especially in harsh environments like the sea, comes from this unique chemistry. Seawater, instead of degrading the concrete, took part in the reaction. The sulfates present in seawater reacted with the aluminum in the pozzolana, forming minerals like tobermarite and chloride-containing calcium aluminate. These minerals filled the pores of the concrete, making it denser and more resistant to the penetration of corrosive substances over time. In addition, this composition gave Roman concrete an impressive self-healing ability. Small cracks that appeared over time could be healed by the continuous reaction of lime with water and pozzolana, forming new crystals that close these fissures. This means that over time, Roman concrete, under certain conditions, became even stronger and more impermeable. But did this magical concrete have no disadvantages? Well, despite its incredible longevity and resistance in marine environments, Roman concrete had some limitations. Its compressive strength, although relatively good, generally did not reach the levels of modern high-performance concrete. And more importantly, its tensile strength was very low, just like that of any ceramic material. This means it was excellent for supporting compressive loads in domes and arches, but not for withstanding forces that pulled or bent it. For this reason, Roman structures were generally massive and relied heavily on the shape of the structure to distribute the loads. In addition, the curing process was extremely slow, which would not be feasible for the fast pace of modern construction. And our concrete, what is so special about it that made it the most widely used building material on the planet? Well, modern concrete, which revolutionized civil construction, is mainly based on Portland cement, invented in the 19th century by Joseph Aspdin. Portland cement is produced by grinding clinker, which is a mixture of limestone and clay burned at high temperatures. With the addition of gypsum, when Portland cement is mixed with water, A hydration reaction occurs that forms hydrated calcium silicates and calcium hydroxide. This reaction is fast and efficient, allowing the concrete to reach its design strength in weeks rather than years. The aggregates, such as sand and gravel, along with water, complete the mixture. Today, we also use a wide range of chemical admixtures to overcome challenges, such as superplasticizers to make it more fluid, accelerators or retarders to control the setting time, air entraining agents to improve resistance to freezing and thawing, and many others. The great advantage of modern concrete lies in its versatility and high compressive strength, which can be much higher than that of Roman concrete. But the real game changer was the invention of reinforced concrete. By incorporating steel into concrete, we were able to overcome its low tensile strength. Steel absorbs the tensile stresses, while concrete absorbs the compressive ones, creating a hybrid material that allows for much more slender structures and large spans, which would be impossible with plain concrete. The standardization of Portland cement and modern concrete production also allows for strict quality control and mass production that meets global construction demands. However, modern concrete also has its limitations. Without proper protection, it can be susceptible to degradation processes, such as carbonation, which I have already made a video about here on the channel, and attacked by sulfates and chlorides, especially in marine environments, which can cause expansion and cracking. The production of Portland cement is also a very energy-intensive process and a major emitter of CO2, which represents an environmental challenge. So, which one is really the best? The answer, as is almost always the case in engineering, is it depends on what you need. For long-term durability in aggressive environments, such as marine environments, here, Roman concrete seems to have an advantage. Its chemistry, with slow formation and the creation of stable minerals, especially with pozzolana and seawater, gives it a strength and self-healing capability that are hard to replicate in modern concrete without specific additives and careful design. Now, when it comes to mechanical strength like compression and tension, modern concrete performs better. With Portland cement and especially steel reinforcement, it achieves compressive strength and crucially tensile strength. This allows for lighter and more material-efficient structures for the same load capacity and the ability to build shapes and sizes that the Romans couldn't even dream of. When construction speed is the critical factor, modern concrete is unmatched. Its rapid curing and standardization allow for large-scale construction projects with tight deadlines, which are essential for today's world, and the Romans didn't have the same capability. Time pressure from a construction schedule. In terms of application versatility, once again, modern concrete stands out. With the wide range of additives, we can design concrete for the most diverse applications, from high-strength concrete to lightweight, self-compacting or concrete with specific aesthetic characteristics. In terms of environmental impact, the production of Portland cement is responsible for a significant share of global CO2 emissions. Although Roman production was on a much smaller scale, the use of pozzolans and the slower curing process make Roman concrete potentially less impactful in its manufacturing. By volume, if we ignore the logistics of obtaining the materials, in some cases the search for more sustainable cements, including those with pozzolans, is still an active area of research today. Now, in terms of cost and mass production, modern concrete is a globally optimized solution for cost and mass production, meeting an unprecedented demand for construction. The Roman materials and methods were more local and adapted to regional availability. The perception that modern concrete fails while Roman concrete endures often ignores the context. The Roman structures that have survived are mostly massive monumental works, designed to last often in dry and stable environments. Those that were in marine environments survived because of that special chemistry. Furthermore, they were not designed for the same loads or for the same geometries that we require today. Modern concrete, when well designed, executed, and maintained, can also have exceptional durability. but it is often subjected to the condition. Harsher conditions, more demanding performance requirements, and life cycles designed to be shorter, especially in infrastructures like bridges and roads. The failure of some modern structures is more often the result of design flaws, poor execution, low material quality, lack of maintenance, or overloading, rather than an intrinsic failure of the material. And will the future of civil construction involve a return? The truth is that engineers and scientists are actively studying Roman concrete. Research aims to better understand its chemistry in order to develop new types of cement and concrete that incorporate the durability and sustainability advantages of ancient Roman concrete, but with the high performance and versatility required by the 21st century. If you've made it this far and enjoyed the video, go ahead and subscribe. If you're not subscribed, leave a like and turn on the notification bell. And if you find our content interesting in any way, consider becoming a member to help us keep producing content here on the platform and be featured in our videos. And if you're curious to learn more about the courses we recommend here on the channel, scan the QR code here on the side or check the link in the video description to have access to several opportunities to develop various skills that will make a difference in your career. And you, which of the two types of concrete do you find more fascinating? Have you ever visited a Roman structure that impressed you? Let me know in the comments, I want to know. Right here on the side, there are two interesting video options that you need to watch to expand your knowledge and satisfy your curiosity. And if you want to support us, just leave your like, subscribe to the channel, turn on the bell, and consider becoming a channel member. That's it, engineering enthusiasts. Take care, and I'll see you in the next video.